All right, friends and neighbors, time now for another, well, not a networking video. We're going to do a little math. This time we're going to be talking about number systems. To begin with, what is a number system? Well, it's just some way that we have to represent or express numbers, some kind of notation. Now we're going to talk a lot about digits here in this particular video, but what we want to be able to do is to figure out a way so that we can write down a representation of every single number and do it the same way no matter how big or how small the number is. So it turns out that there are several number systems that we're going to talk about. We're interested in 4 major ones, but hey, there's lots more. There's even one for dinosaurs. So the big 4 that I was talking about were counting numbers or Arabic, binary, hex, and octal. All right, so here's the central component, right? We've got a digit of some kind. And there's a certain number of values that you can put in that digit or in that particular spot. Each number system has a different set of values that you can put in that spot. So with counting numbers, every single digit that you write down will always have a value that ranges from 0 to 9. You can't use any other value in one digit. In hexadecimal numbers, there's actually 16 possible values that you could put in there. But of course it gets a little weird. How do you write the number 10 or the number 16 in one particular digit? Well, you can't. And so the system includes both counting Arabic numbers and then a couple of letters. And what those letters really mean are the numbers 10 through 15. Octal, same idea, but we have a smaller set now. So the octal rules are that we only have 8 possible values from 0 to 7. And binary is just 2. Importantly, all of these systems start counting at 0. We don't start counting at 1. We always start counting at 0. So they have all of that in common. Now, I think one of the big parts of, and maybe one of the fun parts of really understanding something is deconstructing it. So in deconstructing it, sometimes we go, oh, I sort of get it now. So that's what we're really going to do here. So let's take a look at a counting number or an Arabic number. We're going to use the number 5,432. Now, we know that this has got a bunch of digits. And in each one of those digits, the only allowable values are 0 to 9. So that's what you are limited to in your digits. So we've got 4 digits here, and we've got a couple of ways that we can rewrite this or sort of deconstruct this number. We know that it is 5,000 plus 400 plus 30 plus 2, or 5 times 1,000, 4 times 100, and then 3 times 10, and then 2, or 2 times 1. Okay, well, those values can be further deconstructed and written in the form of exponents or powers of 10. So what we wind up with is 5 times 10 to the third plus 4 times 10 squared, or 10 to the second, 3 times 10 to the first, and 2 times 10 to the 0. Anything raised to the 0 power is going to be actually 1. Now the base, the 10, is what really makes these a base 10 set of numbers. And so we can, when we deconstruct this in this way, you know, kind of using that old scientific notation, then it becomes a little clearer why the numbers are structured the way that they are. Okay, so if we keep this in mind, we can actually move on to some of the other number systems. So let's go to octal. We'll up our game a little bit here. So same rules. We've got a couple of digits, whatever they are, but we know that the only reasonable numbers, or not reasonable, the only legit numbers in those spaces are now 0 to 7. Can't use 8 or 9 anymore. So 8 possible values. Now it seems a little weird, so before we dive into this, where do we use octal? Well, we use it in several places, but one of the most common places that you can see it is in file or directory permissions and ownership. You'll see a lot there in file systems. So let's try an example. If we take a number, 1747, and we know that it is an octal number, well, then what we're going to do is switch to base 8, which means that each one of these digits is a multiple or multiplying times one of those powers of 8. So we can start from the right-hand side and say, all right, we're going to go from 8 to 0, 8 to the first, 8 to the second, or 8 squared, and then 8 to the third. And then if we needed more, we could keep going. But in this case, we've got 1 times 8 to the third, 7 times 8 squared, 4 times 8 to the first, and then 7 times 8 to the 0 power. If we sort of expand that a little bit, almost working in the opposite way that we were with the Arabic numbers, then we wind up with 1 times 512, 7 times 64, 4 times 8, and then 7 times 1. Well, add all those up and we get a base 10 number of 999. And that's an early indication of how you might actually convert between the numbers. In this case, we had an octal number that actually used 4 digits, and that converted to a base 10 number that only used 3. All right, let's go for gold here. Let's try hexadecimal. Now that's base 16. Now the challenge here is that we've got these extra letters thrown in that mean these actual different values. What we're going to add, in addition to 0, 9, we're going to say that the letter A is 10, B is 11, and on up to F, which is 15. Everything works the same way, it's just a little weird. So if we have an example hexadecimal number of ABC8, I know it looks weird, but here's how we go. We know that the one all the way on the right is something times 16 to the 0, then the next one is 16 to the first, 16 squared, 16 cubed. What we do is we say, well, all right, we're just going to write it down. A times 16 cubed, B times 16 squared, C times 16 to the first, and then 8 times 16 to the 0. And then we just convert them to the values that we know that they are. So it's 10 times 16 16 cubed, 11 times 16 squared, 12 times 16 to the first, and 8 times 16 to the 0. We keep expanding and we wind up with finally the number 43,976. Now the funny thing is, the bigger your base, the bigger the number you can represent with a smaller number of characters. In this case, we see 4 hexadecimal characters was equal to a number that had 5 base 10 characters or digits. All right, hopefully we got a handle on that. Let's try some binary. Now, you've probably all seen that t-shirt. There are 1-0 kinds of people in the world, those that know binary and those that don't. Well, if you read that as a 10, you're going, but it's actually a 1-0. And so 1-0 in binary, of course, is 2. So in binary, the only valid values that we have per digits are 0 and 1. Now, binary is also, we always say, it's the language of computers or the number system of computers. But in fact, even though this is truly what we use, and a lot of times we use 1s and 0s to indicate voltages or vice versa, we see the use of hexadecimal and octal all the time in these kinds of systems too. So let's take an example of a binary number. We've got it written there, 1011 0010. And I just break it up sometimes among the 4-bit chunks to make it a little easier to read. We also know that all the way on the right, it starts with 2 to the 0. So when you have 8 bits of information, it's 2 to the 0 on one side and 2 to the 7th on the other side. So that's how we deconstruct this. We would do 1 times 2 to the 7th, 0 times 2 to the 6th, and so on all the way down to 0 times 2 to the 0. We expand those out, right? The same way that we were doing before. 2 to the 7th is 128, and so on and so forth. And we wind up with a number that is 178. Now here's just a quick hint for you. Anytime you've got a 0 in that 2 to the 0 spot, you're dealing with an even number. If there's a 1 there, it's going to be odd. Some other things that are good to know when we're talking about binary numbers. When we have 1 bit of information, or 1 digit, that's 1 bit. When we have 4 digits, that's called a nibble. And when we have 8 binary digits, that's a byte or an octet. Well, I think that'll do it for right now. That will keep the video short. It's been a gentle introduction to numbering systems. In another video, we'll talk about how they relate to each other and maybe how to convert between them. Thanks for watching, thanks for listening, and may your packets always reach their destinations. Oh, and let's hope that your calculations are always correct too.